All right, guys, I'm gonna start soon. Um, this is gonna be lesson one. Got some new markers also. Let's see if I can get this to work. So, lesson one, group theory. Oh, let me get rid of these banners. All right, so this will be the first lesson, or the first official lesson in group theory. We talked about monoids briefly. We said a monoid was basically a set. It has this binary operation where you can combine two elements to get a new element, and it had to satisfy certain properties to be a monoid, right? Um, and before I get into the lesson, I just wanted to go over some sources for people that maybe are watching this in the future or watching on YouTube. I think a good source for, I would say, like undergraduates especially, is this book by Jacobson. This is Basic Algebra 1. This has all your basic group theory, ring theory, everything that you would see in like an undergraduate course and even in like a basic graduate course, I would say. This can basically be handled by anybody. Then I would say for graduate students, if you're getting a little more advanced, you may want to go to the classic Dummett and Foote. So this is what we used in our graduate school. I think this is pretty common. It's a good book. It's got a little bit of homological algebra at the end, which is interesting, but the rest of it's like pretty easy to digest for any graduate student, I would say. And then if you go to the extreme, or it's not even really that extreme, I would say, but for more of the advanced students that have already basically mastered Dummett and Foote, you can look at some of this algebra stuff from a category theory perspective, and that this algebra chapter 0 by Paulo Alufi is a good source for that. Yeah, Alufi is good. Yeah. Yeah, this book is excellent. Highly recommend this book, especially if you're really interested in like category theory, sort of like what your question was aimed at. You're probably interested in this book. Well, yeah, you obviously are, because you already said you are. Right. So those are basically the three sources I'll be using. I might not use the exact language from any of them, but I'll be taking exercises from them, and I'll be sort of using the language that's used in those. Dropped something right here. 1 second. Right. I'll kind of stall until we get to 4 p.m. exactly, but yeah, so Luffy is the GOAT. I like these comments. Right, so let me just refresh before we hit 4 o'clock. Let me refresh what we were talking about last time with lesson 0. So we basically just defined what a monoid was. Monoid was this structure. In this, structure is kind of vague, right? So if we're being more specific, it's a set. So a monoid is a specific type of set. We can call that set M. And in addition to M being a set, we also have a binary operation on this set, meaning that there's a function star which maps from M times M into M, meaning that I take in two elements and then I send them to the product, which we usually write as this A star B. Right, so if anybody remembers their Cartesian products, right, if you have a Cartesian product of sets, that just means you take one element from the first set, one element from the second set. And so this function tells you take these two elements and it tells you how to combine them to get a new element in M. Right, so M is a set, it has this function, and the function has to satisfy the two axioms for monoids, right? There has to exist a unit, 1, and this element 1 is the element that when I apply this binary product to any other element in either direction, either on the left or the right, I just get back the same element. So if we had any element like A and I multiplied it by 1, I should just get A. Or if I start out with 1 and I multiply on the right by A, I still just get A. Right, so there has to exist this identity element, which is identity under multiplication, under this product. And then the second axiom is the associativity, right? So we need that A star B star C is always the same product as A star B first. And then we apply the result of A star B to C. And this product should be the same as if we associated the brackets in a different way, if we do the B times C first, and then we multiply by A on the left after. All right, so yeah, that's kind of like a review of what I went over last time, which is just kind of defining, what is a monoid, right? It's this set with this extra structure. And then we can start getting into what a group is. But yeah, is there any questions before I start? What is infinity monoid? I think I need a little bit more context. Are you talking about in like algebraic topology? Are you talking about like the infinity category notion, like infinity monoid? Because in that case, I would assume that what you're asking is it's just a monoid. It's a monoid, so it's a monoid. It has the monoid structure, but it's in this infinity category situation, which I think is a little more complicated than what we're doing now. But yeah, you can have monoids in different categories too. So that is interesting. Like you can have a monoid in groups. You can have a monoid in different categories, basically. So our normal notion of monoid is just like a standard monoid. It's a monoid in the category sets, right? This is just a set function. But if you had extra structure on this product, then you could define monoids more generally. Like you could have monoids in sets, monoids over a different group, or you could have, basically monoids in any category you could think of. But yeah, that's another good question. Yeah, so that's getting kind of close to my research too. So that's like infinity categories and operads and infinity operads, right? But yeah, I'm gonna stick a little bit less technical than that. We're just gonna stick with basic stuff for now. So we have this definition of a monoid. It's this binary product on a set. It has an identity and it has an associative product. Then we talked about the definition of a group. So a group is basically a monoid with one extra property for the binary operation, which is that all the elements need to be invertible. So a group G is a monoid. So in particular, it has a binary operation. The binary operation, it has there is an identity for the binary operation, and then there is associativity. So this is just one extra property we're adding to that. So it has all of that stuff plus one extra property, which is that all the elements need to be invertible. And we'll define what that means in a second. But so group G is a monoid Group G is a monoid, and in addition, it's true that for every U in the group, again, if you're just watching this and you don't know what this symbol means, this is just set theory. This is an element of, right? So this is saying, in addition, it's true that for every element U in the group, it's true that there exists another element, which we'll call like V. All right, that's a little maybe hard to read, so I'll call it U prime. So if for every element U, there exists a U prime, also in the group, such that when I multiply the two in either order, I get the identity element. So U times U prime is the same as U prime times U, which is 1. All right, so a group G is a monoid, and in addition to being a monoid, it's true that for every element U in the group, there exists a U prime also in the group, and when I multiply these two elements together, I get the identity, no matter which order I do it in. So another definition for this U is we say that this element in the monoid is invertible if it has this property, if there exists this U prime that inverts it to get back to that identity. So we say U is an invertible element, or is invertible. So it's invertible under the monoid product, meaning exactly what it says here, that there's some other element that when I multiply them, I get the identity. All right, so yeah, groups are basically these additional structures, right? They're monoids, so they have these associative products, they have identity, but they also have the additional property that's very useful. It turns out that all of their elements are invertible, meaning that multiplying by an element can essentially be undone by multiplying by this inverse element, by the U prime here, which we'll eventually be calling U inverse. But first we have to show that actually this inverse is unique, because that's not obvious here. It just says there exists a U prime, but it doesn't necessarily need to be unique. It just, there exists one, maybe there's more, maybe there isn't. But we can actually show that this U prime is unique, and then we'll just write it as like U inverse, or U to the -1 power. Okay. Any questions? I like the questions so far, so definitely keep them coming. I just can't get too off topic. We can definitely talk about infinity monoids at another time. I'm just not prepared to talk about that right now. So, right. So, what are some examples of these groups? Right. We talk about monoids. We gave some examples last time, I think, which was like you have the multiplication product for non-negative integers, for instance. That's a monoid. And if you include 0, it's actually not every element is invertible, right? Because when you multiply 0 by, say, 1, you get back 0, and there's no way to invert that. Right. All right, so let's give it another example of a monoid, but in this case it'll be a group because every element will be invertible. And so what is an example of that? Right, so we've defined what group is, right? But we haven't given any examples yet. And actually, in some sense, this example of a group will actually sort of be containing all examples of groups in some sense, as I'll talk about in a little bit later. But that's the symmetric group. So the example is example and a definition, I guess, which is this Sn, usually written like this. So this is the symmetric group on n elements, or usually it's the numbers 0, 1, 2, up to n minus 1. or 1 through n, either way. Yeah, so Sn, how do we define this? This is the, yes, exactly, yeah. I see it in the comments. Yeah, permutations. So this is the permutations, or in other words, they're bijections of a set with n elements to itself. So usually, or not usually, but let's say that n equals 3. So we have the elements 1, 2, and 3. This light's a little bit in the way here. See if I can move that. No? No, it's worse. Wow, it's like right in the point you can't see it. All right. Well, I'm trying to write 1, 2, 3 here. So, for example, when n equals 3, you have bijections of a set with 3 elements to itself. So basically, you're just saying, okay, where can 1 go? I just have to specify what the output of the function is. So let's say 1 goes to 2, 2 goes to 1, and then 3 has no other option but to go to 3 because it needs to be a bijection, which means it has to be 1 to 1 and onto. So I can't send 3 to anywhere I sent any of the other elements, so there's only one other option, which is I send it to 3, right? So this defines a bijection on the set with 3 elements, and that gives us an element of S3. And another way to write this element would be basically just turn this the other way. So you have 1, 2, 3. 1 is getting sent to 2, 2 gets sent to 1, and 3 gets sent to 3. So sometimes you'll see this notation here. There's also cycle decomposition notation, which is another way to write this. I won't go into that right now, but this is the most straightforward notation because this shows you like explicitly what the bijection is. It says 1 goes to 2, 2 goes to 1, and 3 goes to 3 here. So there's no ambiguity, you know exactly what the permutation is. And then for it to be a group, there needs to be a product, right? So what is the product here? Composition of the bijections, right? Because if I have 2 bijections, F and G, I can compose them to get a new bijection, right? So F comma G basically gets sent to F composed with G. Or in other words, if G is a bijection and F is a bijection, I can apply the bijection G first, then apply F after, and this total map, the composition of the 2 maps, defines a new bijection. And that allows us to take 2 separate bijections and basically combine them to get a new bijection, which is the product. Okay, so this is your standard permutation group, and like I was saying before, in some sense, this permutation group is containing all other groups in a sense. And we'll be able to prove at some point, I don't know if we'll do it today, but every group embeds as a subgroup inside of some Sn, where n just has to be the size of the group. So initially, it seems like these Sn are just, a particular type of group that we can define, but later we'll actually show that every group can actually be embedded as a subgroup of this. So it actually is special in some sense. Right. So we have a group. It's the monoid product is this composition of the maps. When you compose 2 bijections, you get a new bijection. And you can kind of do the math out from this notation here. If you have 2 of these types, you can just follow like 1 goes to 2, and then you can look at the next bijection and see where 2 goes, and follow that way, and you can compose these bijections pretty easily. All right, so let's just do a quick example of composing 2 bijections. So for instance, let's say I have sigma 1 here, the first bijection. Let's say 1 goes to 2, 2 goes to 1, and 3 goes to itself. And let's say we have another bijection, which is sigma 2. Let's say now 1 goes to 3, 3 goes to 1, and 2 goes to itself. I got a question. So what about group of rotations? To what permutation group is it isomorphic? Okay, so that's a good question. I'll get to that in a second. Let me just finish this example. So we have sigma 1, which is defining one permutation or one bijection from the set of 3 elements to itself. And then we have another bijection. And so the composition product says we should be able to combine these in some way. So I should be able to do sigma 1 first and then compose it with sigma 2 after, right? And I should get a new bijection. And we can actually compute what that bijection is from this very easily because we're doing sigma 1 first, then sigma 2. So 1 gets sent to 2 by the first bijection, and then 2 gets sent to itself. So in total, 1 is just going to 2. And then 2 goes to 1, which then gets sent to 3. So in all, 2 gets sent to 3 by this composition bijection. And finally, 3 goes to 3 in the first bijection, but then 3 gets sent to 1 in the second bijection. So 3 gets sent to 1. And you'll notice there wasn't really much option for 3 because it's a bijection and we know 1 got sent to 2 and 2 got sent to 3. 3 necessarily has to be sent to 1. There's no other option. Okay, and then the question from the chat was, what about the group of rotations? To what permutation group is it isomorphic? Right. It's a very good question. And we'll see. So the thing that allows us to make that statement is actually Cayley's theorem. And so I'll kind of just give a brief, really brief overview of what Cayley's theorem is saying, because Cayley's theorem is actually probably one of the most important theorems in all of group theory. Right, so here, let's say, so group of rotations. Wait, when you say group of rotations, are you allowing flipping the, with the, changing the orientation? Oh, group of rotations of a circle. Oh, okay, yeah, so I should have specified that we're only talking about finite groups right now. Technically, it's still true for infinite groups, but then we have to talk about what is the symmetric group on an infinite set. And if it's uncountably infinite, like in your case, then it's going to be like the symmetric group on an uncountable infinity, which is going to be like one power set even higher than the cardinality of the reals, I believe. So yeah, now you're getting into like sort of let's just stick to finite groups. And in the case of finite groups, the statement is that you can always embed a finite group into some symmetric group. You can do it in the infinite case too, but then you're just going to be in an infinite symmetric group, so it's kind of confusing. Well, no. Cayley's theorem actually works for infinite groups too. It's just that you're going to be... the statement just isn't really saying a whole lot because you're ending up with the subgroup of some gigantic symmetric group, which is like the symmetric group on some huge set. Right? So you get this gigantic group, and then the theorem just says it's some subgroup of that. Okay, well, that doesn't really help much because the group is like so gigantic. But if you had like actually, let me just talk about the dihedral groups for a second. So, because this is what I thought you were talking about, which is like if you have a regular polygon, if it's four-sided, what you have a group of rotations, so you can rotate by 90 degrees. You can rotate by 90 degrees twice, then you'll get 180 degrees, or you can do it 3 times, and you'll be 270, and then if you do another 90 rotation, you'll be back at the beginning, right? Or you can also do a reflection about some axis of symmetry, right? So in total, there'll be eight elements of the group. There's 4 rotations, and then I can do the 4 rotations along with a flip of the orientation. So the symmetries of the square, right, this has 8 elements. And in general, you can check the book in Jacobson for a proof of this, or you can look online anywhere. But in general, we call these like D2n. So n is the number of sides of the regular polygon. In this case, it's 4. And it's always 2n because you can show that this dihedral group, which they call it, always has twice the number of elements because of this flip symmetry here. Right, so we have the 4 rotations, and then we have the 4 rotations with the flip, and that gives us 8 total elements. And so the Cayley's theorem in this case would say that this dihedral group, which has 8 elements, is some subgroup of S8. But S8 has how many elements? I don't know if that person's still watching. So we have a group with 8 elements, right? And so Cayley's theorem just says that this group is isomorphic to, or equivalent to in some sense, to a subgroup of S8. But S8, the symmetries of 8 elements, has, you know, a lot of elements. There's 8 factorial elements because there's a lot of different bijections you can get. But DA only has 8 elements, right? So it's isomorphic to an 8 element subgroup of S8, which actually has 8 factorial elements. So it's a very small subgroup compared to the entire S8. And you'll see that Cayley's theorem in general gives you results like this. It'll say, yeah, your group is isomorphic to the subgroup of some symmetric group, but that symmetric group is like usually as big as possible, meaning that it contains like, it's a symmetric group on every element of the group. So if you have 8 elements in your group, it's going to be a symmetric group on 8 elements. And so you're going to get this, it's going to be a subgroup of this massive S8 group, which has 8 factorial elements, which is 8 times 7 times 6 times 5, etc. Okay, so yeah, all of that to just basically say that we have this is a common group that's studied, which is the symmetries and reflections of regular polygons. In the case when n is 4, you get the dihedral group with D2 times 4 elements, which is 8 elements. And yeah, and then Cayley's theorem would give you this statement about it being a subgroup of S8. I'll probably talk more about Cayley's theorem next time because I don't want to say too much about it too quickly. I don't want to confuse anybody. I'd rather just take a whole hour to talk about it because it's that important. But yeah, so we have definition of group, example of a group, which is these symmetric groups, which is basically the most important type of group. We also have these dihedral groups, which are also important. I would say maybe not as important as the symmetric groups, but also quite important. Right. Yeah, I guess we'll state Cayley's theorem, or maybe let me define what a group homomorphism is first, because I didn't actually write that down, but I think that needs to be stated first, or else Cayley's theorem doesn't really make sense. I do like these questions, though. Definitely keep the questions coming. These are good questions. Right. So first, let's just talk about what a group homomorphism is. So a function between two groups will be a homomorphism of those groups, or in other words, like homomorphism, what does that sound like? It's a morphism, so it's a transformation, and homo means that it's of the same type. So you have a group on one side, you're transforming it into another group, which is of the same type. So a function, say phi from G1 to G2, where G1 and G2 are groups, is a homomorphism. Actually, let me take the exact, because I didn't write this down. Let me take the exact entry from Jacobson. So this is like page, let's see. Yeah, so Cayley's theorem is 1.3 on page 36, and this should be right before that, I'm assuming. No? Where do they define homomorphism? Oh, I guess they do it over here. Yeah, you got it in the comments. Yeah. So basically, it just needs to respect the product, right? So it's a homomorphism if... I just wanted to write down the exact from the definition since I didn't have it in my notes written down. But yeah, it is a homomorphism if phi of G1 star G2. So if I take a product of two elements in G1 first, and then I send it through the map, it should be the same thing as if I send the elements through the function first and then apply the product on the other end of the other group. So the thing here to keep track of that's important though is that this products are actually different products. So here, the first statement is saying if phi of G1 with multiplied in G1 with G2, here you have the output of the function which is in G2, so really here you're applying the product, but the product is in G2, not in G1. So these are two different products. This is product in G1, this is the product in G2. And this needs to be true for every element G1 and G2 in the groups. So if this is true for all G1, G2, and G. So if that's true for every two elements, if I can multiply their products first, then send them through the function, it should be the same thing as sending them through the function and then applying the product on the output. If that's true for every two elements, any two elements I can pick from G1, then we say it's a group homomorphism. So this is just the definition of group homomorphism. Which again, we're just saying it's a morphism, so it's a map, it's some sort of function between the spaces, but it's a homomorphism in the sense that the structures are the same on the input and the output. Let's see. Right. So group homomorphism function, it has to satisfy this extra stuff. If that's the case, then you can prove certain things like the output or the image of G1 is actually a subgroup of G2. So this function somehow preserves the structure. You can map every element through to G2, and because it preserves this product here, you end up with a subgroup on the output. You can also show that it sends the identity of the first group to the identity of the second group, and it sends inverses to inverses. So if I have if I know where G1 goes through the function, then I know where G1 inverse goes because I can just send it through the function first and then take the inverse on the output. So yeah, I'm kind of skipping over a few things. I'm saying a lot of stuff here without writing it, but I'll try to write all this down better for next time. Right, so we have this group homomorphism, and then let me just state Cayley's theorem real quick, and that'll be the last thing we talk about unless anybody has any questions. So Cayley's theorem is going to be a statement about a particular group homomorphism. In particular, we're just going to have any group on the input, and we're going to show that it maps injectively into some symmetric group, and that's going to be the statement of Cayley's theorem. So here, let me be a little imprecise here. I'll talk about Cayley's theorem, but I'm not going to prove it or anything. I'm not going to be super technical about it. But Cayley's theorem is very important, and it's very fundamental for algebra, and it has a generalization called the Yoneda lemma, which is a category theory statement, which is very, very general. And this is just a very special case of it. No, the proof is actually not bad at all. No. I can actually explain the proof really quick, which is basically all you have to do is show that there's there is this map is a group homomorphism. So you take any group, and you'll have the symmetric group on the size. However many elements are in the group, this is the symmetric group on that many elements. And we're going to define, and we'll show it's injective later, or I'm not going to prove it, but it's not too hard to prove. I guess I'll call this like Cayley's theorem homomorphism. So we send every group element. Do you know where this is going? Mr. Person in the comments? What is the definition of the map in Cayley's theorem? So I take an element of the group on the input, and I'm going to send it to some function, some bijection on the elements of G. So here, I'll leave this as a mystery for a second, right? And then to show that this is actually injective and it's a group homomorphism. So showing that it's a group homomorphism, I forget how difficult it is. I don't think it's that difficult. But to show that this is injective later, once you know it's a group homomorphism, you can just prove that the identity goes to the identity. And if the identity is the only element that maps to the identity, then you can show that it proves that it's injective. FG, what is F? So I have symmetric group on the elements of G. So I have all the elements of G, and they'll be mapped to some other element of G, right? So what is the bijection that I send G to, is the question. And I'm not sure what F of G is. Oh, okay, so you're saying F is, yeah, what is F? I mean, I wouldn't expect you to really figure this out off the top of your head, but the bijection is you take this element G, and you're gonna use G to shuffle around the elements of G. So we're gonna produce a bijection from this element G. What is that bijection? I take every element from the group and I just multiply it on the left by G. I think that's what you were sort of saying there, but I'm not sure what the F was. And maybe you have it backwards too, because so it needs to be multiplication on the left too. If you multiply on the right, you can actually show that I think it does something where it sends it to like the opposite category, so it's a little bit confusing. So I think you actually do have to multiply on the left here. So G, we send it to the bijection, which takes every element G. So we have G1, G2, all the way through to Gn. Assuming G is finite here. It could be infinite and this argument still works, but let's just assume it's finite here. So we have all the elements of the group. I've counted them 1 through n. There's G1, G2, Gn. And the bijection is defined by, I just multiply on the left by G. So G1 gets sent to G times G1. G2 gets sent to G times G2. And so on. And in that way, G produces a bijection on the set of symbols that make up G. So in this case, if G is a finite group, there's some n elements. We can just list them. And Cayley's theorem at its foundation is essentially just saying that this is a group homomorphism and it's well defined, and I can just send every group element from the group to the bijection, which is left multiplication. Basically, I just send every element to its multiplication on the left by G. So I have the n elements, multiply all of them by G on the left, and then I get new elements. You can show this is a bijection because G is invertible, and because you're starting with the group here. So you can show this is a bijection, and then you're good. So you have an element of this group, and then again, like I was saying, you have to use the group homomorphism properties to show that this is injective. Well, first you have to actually show that it is a group homomorphism. Then you have to show that it's injective, and then from that you prove Cayley's theorem essentially. So really, it's not too difficult. You just have to first prove. First, you have to prove that this map actually is a group homomorphism, which is not hard. And then the second thing you have to prove is that the identity gets sent to the identity. Actually, we didn't prove this, but you can show that for a group homomorphism, if the identity is the only element that gets mapped to the identity, then you can show that it's injective, and then you'll use that. So you'll prove that phi c of EG is equal to the identity in this symmetric group SG. Yeah, and once you show that, oh, sorry. I'm saying this wrong. I'm mixing things up here. This will prove that it's a group homomorphism, but then you have to show that it's injective, so you actually have to prove that this is the only element that gets sent to the identity. So really you have to show that the kernel of the map is the only thing that gets sent to 0 is the identity in G. Right, so for Cayley's theorem, you define this map here the way I've defined it here, show it's well defined. You prove that it's a homomorphism, a group homomorphism, and then you can show that the kernel, meaning the definition of the kernel is everything that maps to the identity in the output. For this group homomorphism, you can show that the kernel is only the identity in G, meaning that the identity in here is the only thing that maps to the identity here, and therefore, I'll go over this next time, but basically you can use that to show that it's injective. So yeah, Cayley's theorem basically just comes down to proving these two things, and they're not too difficult. But yeah, I definitely don't want to hand wave it, so I'll go over this much better next time. But yeah, any other questions? I think I'm going to call it here. Oh, reconnecting. All right, yeah, I'm having some internet issues too, so I think I'm just going to call it here. If there's any other questions, please write in the chat. I'll try to answer them the best I can, but I'm going to stop the recording here.